Okay, right, well, any questions? Joakim.
Yeah, I have been struggling. I liked it very much, but I've been struggling with the concept that you say that each electron shields one proton, and then you talk about ionization energies, like that is the only remaining field that this final ionized electron need to care about. And then you say this idea with the shell system is just crap, but all those electrons below that ionized electron, they shield, those are the ones that shield the proton. It's just not one by one. They all act as a collective.
Yes.
Yeah, but so for me, I had to struggle with that you say it's crap with the shell model. Because you actually do have shells in each shell.
No, I didn't say that. I didn't say the shell model was crap. I said I don't think I used that word at all. At least I hope I didn't. What I was in, but you would see if they bound in, you got the feeling, yes, well, I'm not surprised, but I didn't use that word. As I said, when they bind in two, that forms the inner shell. Then the next lot to form stability requires another 8 electrons in another shell. And there are subshells within that. So I'm not criticizing the shell model. I'm criticizing the reason why that it was introduced using quantum mechanics. So that there are still like the 1s, the 2s, 2p, and all those other shells. They are still there. There's no question of that.
So I think when I thought back and forth about this, I think I ended up with it has to do with your calculation of the ionization energy.
Yes.
That you take it as a recursive formula where the innermost part is the inner shell.
Yes.
Yeah, and then you add on top of that just the effect of the next ionization energy.
Yes.
Yeah, so that's where you say each electron shields one proton, because that's the recursion formula you use. So it works. It's very accurate. It's like you can do that. But I think what happens in reality is not that you have a separate layer, ionization layers on top of each other. You have them as a collective. And then the result is that you can use the recursion formula, but it's not like that's the way it happens.
Well, yes, I mean, the topic of chemistry is so huge that there's no way that I could go into anything in great detail. The reason
it's really good to have that. It's really good that you got that recursion formula to.
Well, if you listen to that bit where I said that with helium, for example, that the first ionization energy, or the first ionization energy, the 1s2 was about 24 eV, and the second one was about 54 eV. I just say that within that both will, they won't keep to those energies. They'll have an average energy of about 40 eV. Now, I didn't go on and say that in every situation, but is every situation, the various electrons will just within the shells, they'll just interchange each other. It's not that one electron is not by itself screening out. The effect is that one electron screens out. But all of the electrons within a particular shell are just moving around and screening out all of the protons of that charge. One electron doesn't pick on one proton.
That's what I wanted to say. So we don't confuse so that people think that each electron creates a shell for that.
No. Once they're in that potential well, there are no rules associated. It's just a random thing. Whatever happens within that shell.
Yeah.
And they move around, but the net effect is that each electron screens out one proton, but it doesn't screen. It's not that one electron screening out one, picking out one proton and screening it out, and another electron is picking out another proton. They just all mix out, and 8 electrons will screen out the charge of 8 protons.
Yeah. Okay, I can come back. Other people have.
Okay.
In chemistry, when they teach periodic trends, the first thing they teach is effective nuclear charge, which is exactly what you're saying. And the way you work out effective nuclear charge is the core electrons minus the total electrons. You're taking the number of valence electrons, and the one valence electron does shield the next one, which is very similar to what you're describing, Viv. But then all of the other properties, ionization energy, atomic radius, ionic radius, electronegativity, those things, all electron affinity, those all emerge from this effective nuclear charge, which is the screening of the nucleus by the electron energy. So it's what I find myself trying to put all the models together. I have the image of the molecular geometry, the tetrahedral arrangement of the electron pairings around. I'm trying to match all of the kinds of things and putting your ideas together with John's ideas of how these things work. I find myself imagining, when I imagine them in slow motion, I imagine the electrons, these gyroscopes that are linked, but then when they are orbiting the 2 nuclear centers, they're doing it at the speed of light. Then you have to bring in the relativistic.
No, the electrons themselves are spinning at the speed of light, but the electrons move. The whole spinning thing is only moving at quite slow speeds.
Right. The 10 to the 15 hertz.
And
then you see them as essentially as a coherent standing wave pattern, which kind of brings it all together. But it hangs together. It's a beautiful way of thinking about it.
Yeah.
What speed was it? You gave a number of the speed or the velocity of the vibration inside the atom. What was it?
The speed is just using classical mechanics. It's so far removed from relativistic speeds that the speed of, well, it's very easy to calculate the speed of one eV electron. And all you do is, okay, the average ionization, I use ionization energy and binding energy are the same thing. It's just that I just found it easy to talk about ionization energies. All you're doing is working out the average energy and saying, well, that's the average speed with which they move backwards and forwards.
Electron sizes, they're about 100. They're about a couple of hundred Fermi. That's still a lot smaller than atomic sizes. So although they're far too big for the nucleus, how do you explain them getting up to 10 to the minus 10 meters or so in terms of size?
Well, it's just the size of the potential well they're in.
Yeah, but the potential well goes down to, it's a potential well, it's a Coulomb well. So so that's not got a size. I mean, it's got a Coulomb well.
It's got a limitation. I mean, it's the same thing with, in this regard, it's like the planetary model. If you get a planet, you get a comet, for example, like Halley's comet that can go, when you do an enormously elliptical thing, then it will travel a long distance because that's still within the potential well. And then there was that recently cigar-shaped object that the astronomers detected that had such a velocity that came from outside of the solar system. It's just whatever, and where on Earth we're at a particular energy level within the sun, and we're going to move within that level.
One of the very nice things about the quantum mechanical model is that the de Broglie wavelength of the proton and the electron are the same in that model, and you're talking about something which has, as you go up to the p orbitals, which has the same dimensionality that you have from having a perfectly symmetric 1s system and one that has a different size in 3 dimensions of space, the 3 dimensions of space corresponding to the 3 possibilities.
One of the things I found out about the de Broglie model for waves is when I tried to calculate, I may have made a mistake, but when I tried to calculate how many, the wavelength of the de Broglie wave and fit that in, I didn't get integer answers. And I have read others were saying that you don't get integer answers with the the de Broglie wavelength. They're saying you don't get integer answers also with quantization according to angular momentum. It's an approximation, is what I've seen. Now, I'd be quite happy if somebody came along and said, yeah, okay, you do get integer answers for the de Broglie wavelength, but maybe I made a mistake, but I've seen others saying the same thing, that it's, the principle is good, but the accuracy is not quite there.
I remember calculating the thing for hydrogen in undergraduate university, and I remember that did give exactly the right answer, at least for the...
Yeah, I don't have a problem with it. There may well be the situation that does work with hydrogen, but I didn't get it to work with many others.
I haven't done the calculation myself.
Yeah, my original concept was that yes, that the de Broglie wavelength did indeed create a circle. And then I just when I went into it, I found that it wasn't quite like that. And I had heard a lot about, I've read some others were saying, yes, look, it's a good model, but it's not quite accurate. Whereas screening, I'm getting the same answers. As far as traveling within, I make no attempt to say how they will travel. I've just said, look, they will be there. There's nothing to stop all the figure-8 wave function and all of that. I have made no attempt to show whether that happens or not. I'm leaving that up to others.
So in my view, you focus on the bare basics of the mechanics of how everything works in the world. And this is sufficient for you to explain everything that has to do with calculating the ionization energy. But it doesn't describe the covalent structure, how the distance between atoms, between atoms in the molecule depends on the shell structure and so on. So you can't just say that this is the only way to see it. It's better when you look at just the stable atom, but it's not the whole story.
But it doesn't contradict any of those other models that you're describing.
Yeah, I agree. I mean, I gave one example. I just don't have the time to go through. So to go through everything in chemistry, this would take at least half a dozen of this sort of lecture to do it. I give one example of ionic bonding and one example of covalent bonding and one example of metallic bonding.
I think that the way you describe the structure of the nucleus, we could try to do the same for the atom. But then the scale is so difficult. You have the overlap with the nucleus. It's a 1/1000th of the wave that you illustrate.
Well, I'll put it this way: the wave equations were only ever solved exactly for the hydrogen atom.
That's also true about the Rydberg equation in terms of predicting the difference between energy levels and transitions. It only ever worked for the hydrogen atom. It doesn't. It's only an approximation for the others. As soon as the more electrons you add, the more the model breaks down due to the complex interactions.
I think it would this presentation would suit very good into a school book. Everything you need to know to understand ionization energy, and very accurate estimates. And then on top of that, the problem with the fringe effects like covalent and van der Waal and metallic versus discrete. Then you have to treat the wave property, definitely, I think. Otherwise, it would be a lot of different trajectories you need to simulate and take parts of.
Well, one of the things I wanted to get across is that when you postulate that electrons forming pairs is the reason for chemical bonding, yeah, it is correct, but it doesn't give any idea of the power of that. And all I'm suggesting is that by the time you throw in the fact that angular momentum is so powerful. I think it gives a much better indication of what's going on.
It's a much better start to look at angular momentum, and you actually have to treat the electron pairs rather than each electron individually.
And also, if you imagine these things traveling at the speed that they're traveling, 10 to the 15 cycles around per second, and they mutually negatively charged, they're going to find their lowest energy configuration, which is at that speed, it's going to what's going to amount to a resonant, coherent, standing wave kind of pattern, which is what's going to yield these minimum energy geometries, which is why molecules form tetrahedral arrangements or trigonal planar arrangements or linear arrangements in order to minimize those and to find those lower energy configurations. So it seems to work very well in my mind.
Arnie and I had a quick chat before about it, and he was explaining how he was already working out and explaining to me about how this model enabled him to get a reasonable understanding of why bonds were at particular angles and that sort of thing. Like I said, I can just present the basics. I think my own impression is I think people would find it easier to work out what's going on when they're using this model than a set of wave equations which has only ever been solved for one atom.
I think there's one weakness in your presentation, and that's this concept of exchanging angular momentum through photons in the model, in the pairing mechanism. How do you see this propensity, this requirement of electrons to exchange angular momentum through photons in pairs? How is that? How do you see
when the photon that is the rotating electron moves in the circle, it is it is physically necessary for that photon to be continually emitting and absorbing photons. Now, they are always attached with it, so that they will always get the same mass, but those photons can then just turn around. Photons are everywhere. You just cannot get any, except by getting a little bit of somewhere and cooling it down to absolute zero. You've always got photons.
Yeah, but those photons could, in principle, interact with any other. Why the electron pairing specifically within the way that you're thinking about it?
Well, I am unable to come up with any other means by which electrons can exchange angular momentum. All photons that are emitted by electrons are circularly polarized, so they have that intrinsic angular momentum of h bar. The rate at which the angle at which they are absorbed gives a mechanism for changing angular momentum. And one of the other things, of course, you've got to bear in mind is as soon as you get down to very, very low temperatures, then electrons or atoms don't start behaving or don't keep behaving the same way as they do at elevated temperatures. You get Bose-Einstein condensate and many other things going wrong, making a difference.
I think that's part of the key here. If I'm thinking about in the same area that you're thinking about here, I'm thinking about the electron pairing in the inner shell of helium, the small atom of helium. There's a dielectron there. So not so much that you have photon exchange between the two systems, but the reason that you have such strong pairing between these two things is because they're a resonant, coherent, harmonic system with the same vibration, with the same de Broglie wavelength, but paired in such a way that they are a boson. So the dielectron is a boson system. And I'm not really thinking about photon exchange or quantum electrodynamics in any way, shape, or form here. I'm thinking about you talked about the electric charge of the two electrons, but there's also the magnetic field of the two electrons at that level as you begin to go inside the rotating photon model. And those can act on another and cancel, giving you a very, very much more stable gyroscopic system, which is a bosonic system. And I think as soon as you do that, then you have a good reason for the electrons hitting in pairs. And then from then on, your model kicks in. And the reason for all of those coupled things is the fact that you're forming bosons, that you're forming dielectron bosons in each of these things. And those dielectron bosons are also a gyroscope. They're actually a paired gyroscope, but doubly spinning through each other gyroscope.
I will agree that, I mean, not enough is known at this stage about magnetic fields, but I would also agree that the photon exchange is not necessarily just the exchange of the electric part, is also the exchange of photons in the magnetic, making up the magnetic part of the electrons as well.
Okay.
I think, Vivian, that would be easier if you went back to how you explained the nucleus, because there you said you had the electric field cancellation, and you have the same here. Why you don't need to talk about photon as the mediator for the electric field cancellation?
Yes, like I said, the first talk I gave, like each of these topics really needs a lecture series in its own right. I just don't have time to cover everything. I'd rather just lay the foundations and leave it for others. I hope you get the main object of the presentation is to show that yes, it is angular momentum that is required to be exchanged. I'm using photons, and I'm not necessarily implying it's the photons associated with the electric charge. The photons also carry the magnetic field, although I don't think that's been quite worked out how that happens yet. But the magnetic fields can also interact, and but whatever way the interaction occurs, you do need some exchange between two electrons to alter their the direction of their angular momentum so that they can travel in different directions. How that occurs, I'm quite sure people. Sean, it'd be an interesting exercise to see how you do that, how you show the exchange of angular momentum.
Well, I don't think there's an exchange of angular momentum. I think that two things are cancelled. One is that charge is cancelled in the hydrogen atom or in any atom, but that charge is cancelled at a radius which is given by a series of shell radii that are
potential
wavelength. But I think that's one thing that's cancelled is charge, and that's charge that's outside about an angstrom, so much bigger than the size of an electron, 100 times bigger than the size of an electron. That's where that kicks in. That comes from the de Broglie wavelength. But the de Broglie wavelength itself is fixed by a velocity which is roughly, say, 4 times 10 to the 6 meters per second, much slower than the speed of light. But nonetheless, that gives a size scale for this thing. And then the other thing that has to be cancelled, and it is cancelled in pairs, in dielectron systems, in bosonic systems, inside the nucleus and inside the atom, is spin. And I mean quantum spin. I mean proper internal angular momentum spin. But in a rotating electron, a proper rotating electron, there are 3 spins. Now those spins align with one another as much as they can to cancel. And 2 of them can align, you're left with 1 left over because you've got the 3 degrees of freedom of 3-dimensional space. So what happens is the spin axis of the flat rotating photon that you would have in a very strong magnetic field aligns with the rotation of the inner photon to produce something which is, well, it's then rotating in a plane, which is the double loop model, and that whole thing tumbles if you're in free space. But I think what you're doing is you're looking at levels of cancellation. And I think you're quite right to say the level of cancellation at spin is even stronger than the level of cancellation at charge, because the level of cancellation at spin is related to, because the rotating photon is still a wave. I mean, it's a Maxwell wave. Is related to the commensurability of that wave internally in the way that the internal parts of that field distribution, which is both electric and magnetic, cancel. So in the free electron, it's the magnetic field that fundamentally cancels, mostly in the external part outside of the electron motion. And the electric field that by necessity, because it's weaker, has to mediate as a monopole with the outside world. But spin is first and then charge. Spin first, then charge. Charge is a weaker consideration, in my view. And the experimental evidence.
That's basically what I said, that it's,
right.
well, you've got charge cancellation, but charge cancellation won't get electrons to drag molecules hundreds of feet into the air in a tree. But angular momentum does have the conservation of angular momentum has a necessary property to do that.
But in terms
Oh, I
of
agree. I
that,
agree with most of what you're saying, John. But
I agree with most of what you're saying too, Viv. But that's the.
I'd like to see you fill it. I'd like to see you fill in the details.
So would I.
Can I show you a little experiment I just made? I have a rotating boson here.
In fact, yes, okay.
So I felt that now when there is a distance between the two spinning wheels.
Mm-hmm.
Yeah, go on. Hey, good for you.
It is a gyroscope effect.
Yeah, you can feel it.
Yes.
You need to be in the same center of gravity.
Is that a wheelchair, or did you make it specially, Joakim?
A folded, collapsed trolley. What?
Oh,
I will admit that you have to say you're not getting very much angular momentum there with wheels traveling.
I know. I wish I could rotate at light speed.
It's come to pieces.
So, but I wonder when they are this distance apart, and I feel the gyroscope effect. Is it because there is a distance between them? Would I cancel the gyroscope effect if they were on the same?
Oh yes, of course. I mean, maybe one thing. Even I mentioned the single flywheel, and let's say you get the bike, you've had on a hand holding onto your handles, and the single flywheel going like a 28-inch bike or a racing bike tire where it's 2.5 feet in diameter or so, and you feel that getting fast, you will have some, if you're just sitting carefully, you'll have some difficulty moving it. But if you stood up and moved your posterior end in one direction, you'd be able to move it in the other direction, or more specifically, if you're standing on a rotating platform and did that, yes, you'd be able to change them. You'd be able to change them a little bit. The conservation of angular momentum, though, is very powerful.
I think it would be nice if you could illustrate that a little bit. I didn't manage to do it with this trolley, but maybe if there were, if you had two gyros that you could show this effect on or something.
It's been demonstrated. It has been demonstrated on YouTube somewhere.
Okay.
There are some very nice videos. We'll get Arnie to post them by a friend of ours, Gary, who's been doing multi-axis motors that can rotate around in 3D. In fact, I want to get him to talk to us at some stage within the next few weeks and show us some demonstrations of some of those things. But Joakim, I love what you're doing there with that with that multiple gyroscope you're putting together there. That's cool. They need a rotating platform as well. We need to put you into space. We have to talk to Elon Musk. Anyway, any more questions for Viv about his presentation?
Mine's not really a question, more of kind of a comment. I've been thinking about the oxygen atom, thinking about your model of the fact that two electrons want to pair up for the sake of angular momentum. And if you think about oxygen, it has 1s2, 2s2, 2p4. So if you look at the second shell, it has 2 electrons in the 2s, which are paired up and form the inner shell of the 2. And then it has 4 more electrons in the 2p. So one wonders, why wouldn't they form 2 pairs instead of a pair and 2 singles, which is what actually happens. So I find myself thinking that perhaps when an oxygen atom is in the theoretical situation of being by itself, maybe that's what does happen, which is why it's unstable. Because if you think about 3 pairs of electrons in 3-dimensional space, but one of them is closer into the center, the other 2 won't be able to find a very stable position just on their own unless they split into 3 groups, which is why it wants to make 2 bonds, because then you have that tetrahedral arrangement, although the lone pair is more kind of pulled in, which forces the other 3 to the other side into that. You see what I'm saying? So it kind of maybe explains why, yes, they theoretically could pair, but it's not stable. That's why they prefer to be bonded, because then it puts them into a more stable configuration vis-a-vis that central atom. Does that make sense what I'm saying?
Yeah, the other thing to bear in mind is everything I've shown is in 2 dimensions, but these things are actually in 3 dimensions. And then by the time you try and put those the final two electrons around the, like in the shell concept, around them, the distances start to get quite large. This is attempting to cover the whole field or lay the foundation for the whole field. There's an enormous amount more that needs to be said, and Arnie and John, I look forward to hearing a presentation along the same lines, filling in the gap, so to speak.
I would thank Viv. That was really, it's a fantastic concept, and it makes so much sense. So I really appreciate it. Thank you.
Okay.
Well, Viv, I think we can have a discussion about filling in the gaps in terms of the photon exchange thing, because I think we can do, between us, we can do better than that in terms of having a look at the reason for the boson formation. So for the
I have no doubt that whether it's an interaction, whether you call it interaction of a magnetic field associated with the electrons, or whether you call it photon exchange, it doesn't bother me at all. Same thing.
Okay.
As far as I'm concerned, but at this stage, I don't think anybody's worked out how a magnetic field works properly. They've got the electric field on pretty good. Okay.
Okay, any more questions? Any more comments or questions from anyone?
It's like always when I hear Vivian, everything's so beautifully simple. Then the devil is in the detail. I'm looking forward to more simple presentations. But
if you tune into my gravity sections, you'll find again Einstein's general relativity in terms of space outside matter becomes somewhat simpler to understand, and you should be able to extend his calculations. They are not complex topics, right? Quantum mechanics, well, you've seen nuclear physics. I think you can find out it's relatively easy to work out the structure of any nucleus, the structure of many of the properties of any nucleus of any A and Z. You've seen this. Yes, I think it is simple. Yes, was my terminology necessarily correct? And John, I was talking to John at some stage or other, and I was using the wrong pronunciation of a word or two, and all he had to say, yes, well, I can definitely see you've done this all by yourself. Otherwise, you'd use the terms, pronounce them the way everybody else does.
It's like when you take us from the ground up, from the model of the electron to all the way to the universe, you kind of leave a trail of research topics behind you.
Oh, I mentioned to John that what I'm talking about is just a small fraction of what I actually know, but I'm getting across the principles in the hope that somebody will at some stage recognize. I don't maintain that everything is entirely correct. Photon exchange, yes, I probably created the impression that that comes about from a charge, but again, it's equally coming about through the magnetic field, which is even stronger than a charge. Somehow, some interaction has to occur to enable the electrons to change their direction because of the very powerful nature of the electromagnetic moment. How that occurs, I'm quite sure there are people out there who can fill that in better than I have.
I don't think you necessarily need to have them changing the direction. What do you think about? They're going one way, then they go the other way. But I think the whole thing...
they can actually, as long as they've got some physical contact somewhere. There's nothing to stop them from moving in circular trajectories and all that sort of thing. All those are possible as long as they have some form of physically interacting.
I think the physical interaction is really just a matched, like a pair of cogs and gears that have the same, that harmonically have the same harmonic, that are at the same rate, moving through one another. I think that's the matching.
Well, they still need some way of recognizing that they're in this pair, in this arrangement. How that, at one stage I was thinking it was similar to Cooper's pairs, but I'm not so sure now. I think they are a different way of doing things.
Did you have time to watch my presentation from last week in terms of?
Yes. That's why I'm not sure.
Okay, fair enough. Right, and any more questions from anyone in the?
The teaser slide, the last slide, will you give the remaining presentations this year, or what will happen?
Well, you can ask Arnie and John already have my one on gravity and space-time outside matter, which is gravity we already know. So you'll have to talk to Arnie about when he can finish editing it, and John about when I'm presenting it.
That'll probably happen before, that one will happen before the end of the year, certainly, Joakim. So look forward to next month's exciting episode on that.
Yeah, I think you'll be surprised at really how simple Einstein's, how easily one can reproduce or match the calculations achieved by Einstein in many of his space-time outside matter, and you'll find out he's made one. What he thought was the greatest mistake of his career wasn't.
Exactly.